welcome to the Explainer. We've all seen them, those huge, graceful giants spinning on the horizon. But have you ever really stopped to think about how they capture something you can't even see, the wind, and turn it into the electricity that powers our lives? Well, today we're going to crack one open and find out. So here's our game plan. We'll start with the basics of modern turbine design. Then we'll trace the journey from a simple breeze all the way to a usable watt of power. After that, we're going to break down one of these giants piece by piece. We'll also tackle its biggest weakness, what happens when the air is still, and look at the seriously cool ways we store that power. And finally, we'll look ahead to the future of wind energy. All right, first things first, these are definitely not your classic, old-fashioned farm windmills. Nope, these are incredibly complex engineering marvels, and pretty much all of them fall into one of two main design categories. On the surface, it seems almost laughably simple, right? The wind blows, the blades turn. But the magic happens in turning that simple, slow rotation into stable, grid-ready electricity. That's a fascinating story of physics and engineering. So let's get into it. Okay, so it really boils down to two main flavors. Over on the left, you've got the horizontal axis turbine, or HAWT for short. This is the one you see everywhere, the classic three-blade design. And there's a good reason for that. It's just super efficient at capturing wind energy. On the right, we have the vertical axis, or VAWT. Now, its big selling point is that it's omnidirectional. It doesn't care which way the wind is blowing, which is a neat trick. So whether it's a horizontal or a vertical setup, the mission is exactly the same. Turn wind into watts. So now let's follow the energy, step by step, from a gust of wind all the way to the outlet in your wall. It's actually a really elegant 5-step process. So first, the wind's kinetic energy gets those huge aerodynamic blades moving. This spins a low-speed shaft. Think of it as this slow, powerful, steady rotation, maybe 30 to 60 times a minute. But that's way too slow for a generator. So step 3 is the gearbox. This thing is the MVP. It acts just like the transmission in your car, taking that slow, heavy rotation and cranking it up to a blistering 1800 RPM. That high-speed shaft is what spins the generator. And boom, mechanical energy becomes electrical energy, which then travels down the tower and out to the grid. Now, that 5-step process depends on some absolutely incredible hardware. To really get it, we need to take a tour of the turbine itself. So let's build one starting from way down deep in the ground. Everything, and I mean everything, starts with a part you will almost never see, the foundation. We're talking about a massive, buried block of reinforced concrete. This is the unsung hero that anchors this towering structure and keeps it standing strong against incredible forces. Then, of course, you've got the tower, which is usually made of these huge steel sections. So why build them so incredibly tall? Well, it's simple. Wind is faster and way more consistent the higher up you go. Getting away from the ground-level turbulence is key. So basically, height equals power. Now we get to the really interesting part, the nacelle. That's the big box at the top. You can think of it as the brains and the brawn of the whole operation. It's where all the magic happens. You've got the gearbox and the generator, of course, but you've also got a sophisticated control system that's constantly monitoring the wind and adjusting the turbine's direction and even the angle or pitch of the blades to catch the most wind. And naturally, it's got a powerful brake system for emergencies and a cooling system to handle all the heat. This brings up one of the biggest surprises for people when they learn about turbines. You look at those gigantic blades and you just assume they're solid, heavy chunks of something. But they're not. They are an absolute marvel of material science, mostly hollow, but incredibly strong. And the way they're made is just wild. It all starts with two gigantic, perfectly shaped molds for the top and bottom halves. Inside, workers carefully lay down sheets of high-tech fabrics, like fiberglass or even carbon fiber. Then they seal the whole thing up, create a vacuum, and suck a special resin through all those layers. The two halves are then cooked to harden, glued together with an insanely strong adhesive, and finally, they're finished, painted, and put through rigorous testing. It's this whole process that creates something so light, yet so strong. But of course, it's not always a windy day. And that brings us to the biggest, most fundamental challenge for wind power. What in the world do you do when the wind just stops blowing? Yeah, there's a technical word for this, intermittency. It just means the power source isn't constant. See, unlike a gas or a coal plant that you can basically switch on whenever you want, a wind farm is completely at the mercy of Mother Nature. And that makes it an unreliable source of power if you don't have a backup plan. And intermittency isn't the only hurdle. Just like any massive infrastructure project, wind farms have other things to consider. You've got the noise they produce, how they look on the landscape, and of course, their potential impact on local wildlife, like birds and bats. These are all real challenges that have to be managed carefully. So how do you solve a problem like intermittency? Well, it's simple in concept. You don't let that energy just disappear when you don't need it. You save it for later. You store the storm. This is where energy storage comes in, and some of the solutions are just plain brilliant.
And look at all the different ways we can do this. You've got massive battery farms, which are getting more and more common. There's an old school classic called pumped hydro. You use cheap excess wind power to pump water up a mountain, and then when you need the power, you let it flow back down through a turbine. It's like a giant natural battery. You can even compress air into underground caves, store energy in a super fast spinning flywheel, or get really futuristic and use the electricity to create hydrogen gas. You're basically turning electricity into a physical fuel you can store indefinitely.
So when you take all this amazing technology, the turbine design, the advanced materials, the clever storage solutions, and you put it all together, what does that tell us about the future of wind? Let's wrap this up. So here's the bottom line. Wind turbines are so much more than just modern windmills. They're incredibly sophisticated machines that rely on cutting-edge materials and manufacturing. And yet, their biggest challenge has always been intermittency. But as we've seen, energy storage is rapidly turning that weakness into a solvable problem. And all of that makes wind a crucial player in helping us move away from fossil fuels and protect our environment. And that leaves us with one final massive question to think about. We're already building blades that are longer than a football field is wide. As these giants get even bigger and more powerful, we're going to face a whole new set of challenges. How on earth do you transport something that enormous? How do you even build it on site? And maybe most importantly, what do you do with these colossal structures when they reach the end of their life? The answers to those questions are going to define the next chapter for wind energy.